Hi everyone, welcome to this video. I'm Yuting Shen from Eindhoven University of Technology. In this video, I'm excited to demonstrate you a dynamic temperature sensor with fully on-chip corrections. A temperature sensor is a device designed to measure and detect temperature variations in its surroundings and convert this information into a readable output. Let's firstly look at the setup. Here we have a small PCB board with two temperature sensors, each enclosed within a 3D printed box for protection. Next to it, there is a FPGA acting as an interface between the temperature sensors and the computer. This setup allows us to control the temperature sensors and read their outputs on our computer screen. In this work, we implemented a dynamic resistive temperature sensor in 65nm CMOS technology. Normally, for temperature sensor ICs, the output has large variations due to manufacturing imperfections and thus requires correction. In this work, we smartly integrated this correction in analog domain with minor overhead. This results in a temperature sensor with a remarkably small area of just 0.0023 square millimeters and an energy consumption of less than 3 picojoule per conversion. To put this into perspective, a 1 euro coin covers an area of approximately 400 square millimeters, which could cover over 180,000 of our ICs. Additionally, a single AA battery usually contains 10,000 joules of energy, enough to support more than 3 times 10 to the power of 15 operations of this sensor. If the technical details seem to be a bit overwhelming, don't worry. Anyway, I'm going to show you a very small and ultra-low power temperature sensor. On the right side of the screen, there is a graphic representation. Once we start the measurement, the outputs of the two sensors will be displayed over time. On the left, there is a control panel where we can adjust the settings for both ICs. For instance, if we want to view the result without any corrections, we can input all zeros. Then apply the settings and start measurement. As you can see, sensor A, shown in blue, shows a temperature of around 4 degrees, while sensor B, represented in red, displays -4 degrees. Apparently, these readings are incorrect since it is summer right now. Now let's activate our on-chip correction function by inputting sample values here. After activating the on-chip correction function, the outputs of the two sensors are now combined, displaying a room temperature of around 33 degrees. It's also possible to intentionally introduce an offset value by entering an offset value here. For example, we can add an offset on sensor A. Then you can see that the output of sensor A will be higher than sensor B. Now let's try to heat up the two samples using a hairdryer. As you can see, the surrounding temperatures is rising rapidly. That wraps up this video. If you are interested in more detailed information, feel free to check the information box below. Thank you for watching.